5.4 is quadratic equations. We're actually going to solve quadratic equations in 5.4. So before we were asking what is the height at this time, now we're going to be asking questions for in relation to those application problems. At what time is the ball at a particular height? So we're solving problems that look like ax squared plus bx plus c equals some constant d for whatever our x value is. Now we have three options to do this. You have factoring, graphing, and quadratic formula. Algebraically, I'm typically asking for 1 or 3. 2 is really good for checking, okay? But it's a useful tool since you have your calculators. Factoring, you've seen before. You're looking for some values that, when multiplied, will get you the quadratic. So if I have ax squared plus bx plus c, I'm looking for that a value pulled out in front times some x plus m and some x plus n. The values of these this m and this n have to be matching so that they add to b and they multiply to c. And I kept the a out in front because if you pull the a out in front, then you need to have a times m plus n equal to b and a times n equal to c in order for it to be consistent if you FOIL it. So let's take a look at an example. In this case, I specifically chose a to be 1, so I just have x squared plus 3x minus 10, so my b is 3 and my c is a negative 10. So if a is 1, then I'm just looking for m plus n equals 3 and m times n equals negative 10. So because the multiple is negative, one of the values, either m or n, is negative. That's what this is telling me. Because the 10 is negative. Since that's a multiple, one of those m or n must be negative. Now, the only way that we can multiply to 10 is a 1 and a 10 or a 2 and a 5 with integer values. So if I take a look at the difference between 1 and 10, I get 9. Well, that's not 3. The difference between 2 and 5 is 3, so clearly 2 and 5 are my numbers. It's just a question of which one's positive and which one's negative. So if I look at 2 minus 5, I have negative 3, and if I look at negative 2 plus 5, I get 3. So the 2 is the negative, and the 5 is the positive. So I'm going to say m is negative 2 and n is 5. So the factors are x minus 2 and x plus 5. Once you have your factors, it's very easy to check using FOIL that this is in fact the same function. So I have x squared, right, plus 5x minus 2x and then minus 10. So I get that simplified to x squared plus 3x minus 10. Woohoo, it's the same function. Worked. This is going to be the most useful when you're solving for when ax squared plus bx plus c equals 0, because if I know my factors, then what I have is x squared plus 3x minus 10 is equal to 0. When I factor that to my x minus 2 times x plus 5 equals 0, that means either x minus 2 is equal to 0 or x plus 5 is equal to 0. If either of those two are true, then this whole thing equals 0, because 0 times a constant is still 0. So x is either 2 or negative 5. And the values 2 and negative 5 correspond to our x-intercepts for the function f of x equals x squared plus 3x minus 10. When I ask you a conceptual problem, and I ask you, say, when does the ball hit the ground, this is usually what I'm asking for. When does the function equal 0? Because that's usually our 0 is defined by where the ground is. If you're looking for a specific height, you can ultimately arrive at the same type of formula. So if I have a ball traveling in a path of x squared minus 2x in feet, when will it pass the point of 15 feet for its height? So then I'm setting my path equal to a specific height, just like we were talking about. X squared minus 2x is equal to 15. Solve for a 0 on the right-hand side, so I subtract 15 from both sides. Now I have something that looks like what we just solved. So if I try to factor this, 15 and 1 gets me 15, or 5 and 3 gets me 15. 15 and 1 does not have a difference of 2. 5 and 3 do have a difference of 2, so I'm going to use 5 and 3. Again, I'm just trying to figure out which one needs to be negative because I have a negative in front of my 15. So 5 minus 3 is a positive 2. That's not what we have. We have negative 2. So negative 5 plus 3 gets me a negative 2. That's the case. So I have x minus 5 and x plus 3 equal to 0 for my factors. Solve for when is this equal to 0? When x is equal to 5, or when x is equal to negative 3. So in either of those points will correspond to when f of x passes 15 feet. Now, if x were, say, a time measurement, then negative 3 would not make sense physically for an application problem, because if I threw the ball when t equals 0, negative time is not a thing that we're considering. So in an application problem, things like that do matter, right? And in that case, the x equals 5 would be the only one I really cared about, because if it started at t equals 0, or in this case x equals 0, that's the only one that would make sense. But in the context of a function, it's going to have 2 intercepts. What I recommend that you do is graph these on your calculator. The next thing we're talking about is the graphing concept here. So because I solve for when this is equal to 0, the solutions correspond to my x-intercepts of the function graph. So if you graph this function on your calculator, x squared minus 2x minus 15, you'll see that it crosses the x-axis at x equals negative 3 and x equals 5. So we graph these things so we can see what the heck we're talking about, really. But basically what we just did will get us the same results if we were to graph the function and find the x-intercepts graphically. The whole point of the graphing concept here is to allow you to check. If you find your x-intercepts solely by the graph, and that is not how the question is asked, you will not receive full credit, because that's not what I'm asking you to do. Typically, what I want you to find those values using factoring, or what we're about to talk about, which is the quadratic formula, and then check your answer with graphing. Because the nice thing about this class is you can check all of your answers for the most part. You can always look at the graph, you can always plug your numbers back in, you can always FOIL your factors to make sure they're consistent. There's a lot of opportunity for you to double check your answers to make sure that the answer you got is correct. So use that opportunity to make sure that you have the right answer, so that you know you're right, you know you're done. You can also use it to verify max-min. So right, in the previous section we were completing the square to find the vertex, right? So if I gave you that same function, x squared plus 3x minus 10, well, the h, or the x value for my completing the square, is negative b over 2a, which is negative 3/2. Substituting that in, I end up with my standard form as x plus 3/2 squared minus 49/4. So my vertex is at negative 3/2, negative 49/4. Graph it on your calculator. Find your minimum. And it should be negative 3/2, negative 49/4. You can also use your calculator to find your x-intercepts. And we can play with this a little bit in class. And you should see that negative 5 and 2 are your x-intercepts. Check it with your calculator. Your y-intercept, another thing that you can find or verify with your calculator. Right? 0, negative 10, 0, negative 10. You should get the same result with your calculator. If I give you a graph, you can also solve for the function that satisfies that particular parabola. We did this a little bit before, but now you have the context of factors corresponding with x-intercepts that allows you to do a little bit more with this. So this graph of the green curve here, that's my f of x. And from that, I'm trying to determine what the function is. So I'm going to use my x-intercepts, which are negative 3 and positive 2. in order to start to construct this. I know that my y-intercept is at 0, 3, and I know that the function is, that ax squared plus bx plus c, but I have 3 points, so theoretically you could do it with the ax squared plus bx plus c, but I have the x-intercepts, so I'm just going to use those factors, and then I just have to find that constant a that goes out in front, right? So if it's negative 3, 0, and 2, 0, then my m value is positive 3, and my n value is negative 2. So my function is going to look like a times x plus 3 times x minus 2, because that corresponds with the factors that give me those x-intercepts. Then I just use my y-intercept to solve for a. Okay, so at x equals 0, y is equal to 3. So if I substitute 0 in for my x values, I'll have a times what turns out to be a negative 6 is equal to 3. Divide both sides by negative 6. And that tells me that a is negative 1/2. Done. So f of x is negative 1/2 times x plus 3 times x minus 2, which if you simplify gets you negative 1/2 x squared minus 1/2 x plus 3. That is a very useful thing to be able to do. The last way for you to solve these types of equations is the quadratic formula, which you may have learned before, but I'm going to derive it for you using the concept of completing the square that we recently did, so that you can see why it even works. If you complete the square on the general form of ax squared plus bx plus c equals 0, solve for your x value after completing the square, you get your quadratic formula. That's what it is. You complete the square, you solve for x. The nice thing is that you will be able to use it as it is. You do not have to derive it, but I feel that it's important for you to see where it comes from so that you understand why does this work. Because otherwise you're just memorizing a formula, and that's not particularly useful. So first, whenever we complete the square, we pull that a constant out in front, right? So x squared plus b over ax, and then we keep the plus c outside because we don't need to do anything else with it. From there, I complete the square on x squared plus b over ax. So you divide the b over a by 2. That gets me b over 2a. So x plus b over 2a quantity squared. Subtract off my b over 2a quantity squared. So minus b squared over 4a squared. Parentheses outside of that, and then I have the c. I've completed the square. Now I need to solve for x. First thing is subtract c from both sides. Then I have a times this big quantity of x plus b over 2a quantity squared minus b squared over 4a squared is now equal to negative c. That a is outside, so I'm going to divide both sides by a. So x plus b over 2a squared minus b squared over 4a squared is equal to negative c over a. Since I'm solving for x, I'm going to add this b squared over 4a squared to both sides. So then I have x plus b over 2a squared is equal to b squared over 4a squared minus c over a. I want to combine these fractions so that I have less to work with because I'm about to take a square root. So I want to make sure that they're consistent. So we use what I always call the dead smiley in order to do that. So b squared times a minus 4a squared times c all over 4a squared times a, or 4a cubed. So that gets me x plus b over 2a squared is now equal to b squared a minus 4a squared c all over 4a cubed. Since there's an a in every term, I used the green to reduce that, so that gives me b squared minus 4ac over 4a squared. Square root both sides. That gets me x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac over 4a squared. Okay, well, that's the same as taking the square root of the top and dividing by the square root of the bottom. And the square root of 4a squared is 2a. So then I have x plus b over 2a is equal to plus or minus the square root of b squared minus 4ac over 2a. Subtract the b over 2a now from both sides. So x is equal to negative b over 2a plus or minus the square root of b squared minus 4ac also over 2a. Since these have the same denominator, I can combine them. So that gets you what you have probably learned at some point as your quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Ta-da! This allows you to solve any f of x equals 0 where f of x is a quadratic. This is especially useful if your function is not easily factored. If you can factor your function, that is a lot easier than applying the quadratic formula. But the nice thing about the quadratic formula is that it's always going to give you your answer. So if factoring is just not going to happen, quadratic formula will get you there. So let's look at an example with actual numbers. So if f of x is 2x squared minus 4x plus 2, we're solving for when this is equal to 0. If I were to do the same completing the square that we just did and solve for x, which is also something you're welcome to do, you can complete the square, pull the 2 out, 2 times x squared minus 2x. You divide that 2 by 2 to get x minus 1 quantity squared, and then subtract the 1 squared. Plus the 2 outside equal to 0. Now if I distribute the 2, I have 2x minus 1 squared minus 2 plus 2 equals 0, so these guys cancel each other. And I'm left with 2 times x minus 1 squared is equal to 0. Clearly, if x minus 1 is 0, this whole thing is 0, so x is equal to 1 is the solution. If you use the quadratic formula just as given, you're going to get the same result. So 2x squared minus 4x plus 2. My a value is 2, my b value is negative 4, and my c value is 2. So I have negative b plus or minus the square root of b squared minus 4ac all over 2a. So b is negative 4. A negative of a negative is a positive 4. Plus or minus negative 4 squared is 16. Minus 4 times a, which is 2, times c, which is also 2, all over 2 times a. So 4, but 16, 4 times 2 is 8, times 2 is 16, 16 minus 16 is 0. The square root of 0 is also 0, so I end up with 4 plus or minus 0 all over 4, which is just 1. It's the same answer that we got above. And it takes about the same amount of work. It's just a matter of what's more comfortable. One thing to note from this form is that in the quadratic formula, you are taking a square root of b squared minus 4ac. So b squared minus 4ac needs to be greater than or equal to 0 for these values to actually be real, for them to exist. We don't talk about imaginary numbers in this class, so basically for it to exist, for you to have a solution, you need this to be greater than or equal to 0. So that's something that is relatively easy to check when you are going to solve for a 0. If your b squared minus 4ac is less than 0, then the roots do not exist. And remember, these are your x-intercepts. So all that means about your graph is that your graph doesn't cross the x-axis. It's either entirely above or entirely below. And if you graph it on your calculator, you'll see that. We call this value b squared minus 4ac our discriminant because it is the defining factor for what your x-intercepts look like. If it's greater than 0, you have 2. If it's equal to 0, you only have 1, which means your vertex is on the x-axis. And if it's less than 0, you have none. So it does not cross the x-axis. If we look at the example that we just did, right, b squared minus 4ac was 16 minus 16, and we got 0. So we only got x equals 1 as a solution, and if you graph that function on your calculator, you will see that the vertex is on the x-axis. So that's why we only have one root, one x-intercept. Let me give you an example of each other case. So if your function is 3x squared plus 6x minus 5, and you're looking for its x-intercepts, if you solve for b squared minus 4ac, so b is 6, which means that b squared is 36, minus 4 times a, which is 3, times c, which is negative 5. So we have 96. 96 is, of course, greater than 0. So that means we have two values. If you substitute it into the quadratic formula, you have negative 6 plus or minus the square root of 96 all over 2 times a, which is 3, so 6. So you have two values. Negative 6 plus square root of 96 over 6, and negative 6 minus square root of 96 over 6. Two different roots, and you'll see that if you graph the function also. Third example, no x-intercepts. F of x equals 2x squared minus x plus 4. So this is a concave up, right, since we have a positive 2, parabola that's also been shifted up 4, so its y-intercept is at 0, 4, and it's concave up. So this one isn't going to have any x-intercepts. B squared minus 4ac, b is 1, well, negative 1 squared is a positive 1, minus 4 times a, which is 2, times c, which is 4, gets us, that's 32, 1 minus 32 is a negative 31, that's less than 0, so we have no real roots, no x-intercepts. There's no solution to f of x equals 0 in this case. Very last thing, a modeling problem. So if we use the same one that we had before for the ball, 16t squared plus 3t plus 5, when will the ball be 4 feet high, right? This is the whole goal, ultimately, for why we actually learn these things. So we can figure out when is this going to happen. So for this particular one, we're going to look at when is it 4 feet high. So when is my function, negative 16t squared plus 3t plus 5, equal to 4? Subtract the 4 from both sides, so I actually have a f of x equals 0 kind of form. So that gets me 16t squared plus 3t plus 1 is equal to 0. So a is negative 16, b is 3, and c is 1. Solve for my quadratic formula, because that seems like the most straightforward way to go when I have a negative 16 in front. Anytime that a is not 1, factoring is going to be more difficult. Some of you that are more used to factoring are going to find 2's and 3's pretty straightforward, but when it gets much bigger than that, it gets pretty cumbersome to factor. So, substitute that into my quadratic formula. B is 3, so negative 3 plus or minus b squared, that's 9, minus 4 times a, which is negative 16, times c, which is a positive 1, all over 2 times a, which is negative 16. So I have negative 3 plus or minus, if I simplify inside what my discriminant is, I get 73. So negative 3 plus or minus the square root of 73 all over negative 32. If you get a decimal value for these, that's about negative 0.017325 seconds and about 0.36075 seconds. Considering the fact that this is a ball problem and I threw it probably at t equals 0, the only one that I really care about is this one. So about 0.36075 seconds.